Lattice multiplication is an algorithm that is used for multiplying numbers together. It is different from what most adults learned when they were children, so we will do an example and then explain the connection between the two different methods. Compute 47 times 35. To set up the lattice method, we draw a grid. In this case, since we're multiplying a two-digit number by a two-digit number, we'll make a 2x2 grid. Then we draw diagonal lines from the lower left to the upper right through all of the squares. We write the numbers 47 and 35 like this. The way you should think about this is that each square represents a different multiplication calculation. The top left is 4 times 3. The top right is 7 times 3. The bottom left is 4 times 5. And the bottom right is 7 times 5. As we perform each calculation, we will write the result as a two-digit number where the first digit goes in the top left and the bottom digit goes in the lower right. So 4 times 3 is 12. 7 times 3 is 21. 4 times 5 is 20. And 7 times 5 is 35. If one of these calculations happened to result in a one-digit number, we would use 0 as the first digit. So for example, if we had 2 times 4, we would write 0, 8. To calculate the final result, you add down the diagonals starting from the lower right corner. In the bottom right, we have 5. Next, we have 0 plus 3 plus 1, which is 4. Then we have 2 plus 2 plus 2, which is 6. And then we have 1. To read off the final answer, we start from the top left and move around clockwise. The final result of this calculation is 1,645. If one of the diagonals happened to add up to 10 or more, you would carry a 1, just like addition in columns. So at this point, there are generally two questions. The first question is, why does it work? And the second question is, how does it relate back to the more well-known algorithm? So why does this work? Multiplication can be understood as counting up boxes in a grid. So if we looked at the product 2 times 3, we can think of it as a 2x3 grid. The result of 2 times 3 is the total number of squares that are in the grid. So 2 times 3 equals 6. This idea works well for small numbers, but as numbers get larger and larger, it gets harder and harder to keep track of all the squares. For example, for 47 times 35, we would end up with a grid that is 47 by 35 and have to count up all the pieces. The problem is that there are just too many of them to count. So rather than counting up all the individual squares, we're going to break up this picture into pieces that are easier to work with. Specifically, we will break up 47 into 40 plus 7 and 35 into 30 plus 5. And now we'll count up the number of squares in each of the 4 separate grids. 40 times 30 is 1,200. 7 times 30 is 210. 40 times 5 is 200. And 7 times 5 is 35. The total number of squares in the entire rectangle is the sum of the number of squares in each of the 4 separate rectangles. And if we add up all these values, we will get the result 1,645, just as before. Both lattice multiplication and the more common multiplication algorithm are different ways of keeping track of this information. And the idea is to use the place value system to track the digits. Let's look at the grid and look at the lattice multiplication side by side. We will label each diagonal with the names of the corresponding place value system. Ones, tens, hundreds, and thousands. We will draw a chart to organize this information. Across the top of the grid, we will label the place values. And down the left-hand side, we will label the positions. And now we will fill in the digits from the lattice multiplication using zeros as placeholders for the larger numbers. In the top left, we have 1 in the thousands and 2 in the hundreds. And then we will put zeros for the tens and the ones. For the top right, we have 2 in the hundreds and 1 in the tens, and then a 0 for the ones. In the bottom left, we have 2 in the hundreds and 0 in the tens, and then we'll use a 0 for the ones. And lastly, for the bottom right, we have a 3 in the tens and a 5 in the ones. Notice that these 4 values correspond exactly to the 4 values that were calculated in the grid on the right. And that because of the organization, when we add up along the diagonals, that corresponds to adding up according to the place values. And this is why lattice multiplication works. All it is doing is rearranging the information we would get trying to count up the number of squares in the grid into a nice compact form. How does this relate to the other method? We will first talk through the calculation. To do 47 times 35, we start from the right columns and do 7 times 5 to get 35. Carry the 3, and the 5 times 4 is 20, plus 3 more makes 23. And then we bring down a 0 and repeat the process starting out with the second column. 3 times 7 is 21, and we carry a 2. 3 times 4 is 12, plus 2 more makes 14. And then we add these two numbers together. This gives us 1,645. Let's see how these values line up with our grid. The number 235 corresponds to the number of total squares in the second row of the grid, 200 plus 35. And the number 1,410 is the number of squares on the top row of the grid, 1,200 plus 210. And if we think about this a little bit further, we can actually break down our multiplication in columns in such a way that we can see all of these numbers. We can actually see all these numbers arise from multiplication in columns, but it requires us to think about our calculations just a little bit differently. We will start off as usual doing 7 times 5 to get 35. Now at the next step, instead of thinking about it as 4 times 5, we will think about it as 40 times 5, because that 4 comes from the number 47. 40 times 5 is 200. Then we go on to the next step, which is not 3 times 7, but 30 times 7, which is 210. And for the last step, we have 40 times 30, which is 1,200. We can see that the first line of work in the more common algorithm is actually the combination of two different calculations that have been added together. Similarly, the second line of the common algorithm is the sum of the last 2 lines in this other algorithm. All that happened is that they were added together in one step. The purpose of this video is to help you to understand why the lattice algorithm works. The actual idea is exactly the same. It's just that the presentation has been changed slightly. It's not that one algorithm is better or worse than the other. They're just different.